Hey guys, for my problem correction I did number 6, which asked us to find a bunch of quantities for a large Einstein solid. So to begin, it asks us for multiplicity, for which the equation is, or the expression is given in the book. This is specific to a large Einstein solid because there are a few factors that we don't, or there's a few constants that we don't need to consider when we have really high n and q. So to begin, I took the ln of both sides and expanded it a little bit to make it easier to work with. Then I used Stirling's approximation for a natural log to get rid of the factorials. And then I simplified it a little bit, canceled the terms. And then for this expression right here, we can use these two assumptions to convert it by this process from here to here. So essentially I just plugged this in for this expression and got this, and then I canceled the n ln of n's out and ended up with this term right here. So after that, I took away the logs by exponentiating both sides, ended up with this expression, which if you multiply it all out, you get this, which is the multiplicity. So the next part asks us to find the entropy, which now that we have the multiplicity is pretty simple. We know that entropy is k times the log of the multiplicity. So we just plug in our expression for multiplicity and we get this expression, or kind of clearer, this expression. So part C asks us to put the energy of the Einstein solid in terms of temperature. So to start, we already have our entropy, which is this expression contracted, this expression expanded. So we know that 1 over temperature equals the partial derivative of the entropy with respect to energy. So we can just take the derivative of our expression for entropy with respect to temperature, or with respect to energy actually, and we get this expression here. These terms cancel, so by multiplying 1 over t by epsilon over k, we end up with this equation, and then by raising both sides to the e, we get this. And after that, we isolate u, and we get u equals n epsilon e raised to the negative epsilon t, or tk. The last part of this question asks to describe the behavior at high and low temperatures. At high temperatures, T would be really high, which means, so say this goes to infinity, then E, since this is in the denominator, would go to 0, so this entire expression would go to 0. Whereas at low temperatures, E would be raised to an infinitely high negative number, which means that it would just go to 1. So then you just get n epsilon for your low temperature limit. So the last problem asks us to find the heat capacity, and we know that heat capacity is equal to the change in energy with respect to temperature. So basically what we do is the same technique that we use to solve part C. We integrate, or rather we derive with respect to temperature, and that gives you this equation, or that expression. And then it asks you to describe the behavior at high and low temperatures. So if you graph the heat capacity versus temperature, sort of a similar thing happens, except in this case, this t squared in the denominator means that as t gets very little, this will actually go to infinity, since 1 over a very small number is a high number. And then it asks you to describe the high temperature limit and the low temperature limit. And the high temperature limit is when the energy is much higher than the number of oscillators, and the low temperature limit is the reverse of that.